I kind of screwed this presentation up this morning. I think it was because it was too early and I had too much coffee in my system. We'll try it again. What we're going to talk about right now is the placement of electrons in an individual atom. And this is kind of a starting place for learning how electrons distribute themselves in the volumes surrounding the nuclei that they're attached to. When you're talking about individual atoms, the volumes that the electrons occupy end up having very predictable shapes. And we're going to look at what those shapes are like for individual atoms. When you get into larger molecules, it's not so simple, it gets a little complicated. But just keep in mind that right now, we're looking at the very simple case where we have an individual nucleus that's packed with its protons, and we have the electrons that are distributed in the volume around that nucleus. And we're going to look at how those electrons get distributed. And there's a couple of things that we're going to be keeping in mind. And those are quantum numbers. We've got a quantum number for the principal energy level. We'll have a quantum number associated with the orbital angular momentum. And we'll have a quantum number for the spin, and we'll talk about all of these properties as we go. So first of all, the principal quantum number kind of divides divides isn't the best word, but I'm going to use it anyway. It divides the volume around that nucleus into subsections. And those subsections, pardon me for using a graph that looks like the hydrogen atom that we used earlier, that we're talking about something different, but I'm going to use a very similar looking picture. Those subsections are composed of a first section that has a very small radial separation from that nucleus. And we'll call this the, what does your thing say your quantum numbers are for principal quantum numbers? N equals 0, 1, 2, 3, or is it 1, 2, 3, 4?
1, 2, 3, 4.
It's 1, 2, 3, 4. Okay, so we'll call this the N equals 1 level. And all of the different orbitals, this N equals 1 level represents a volume that has whatever this R naught value is, approximate R naught value of separation between the electrons and the nuclei. The N equals 2 level also describes a volume around that nuclei, only the R is larger for that level. And so that volume, the N equals 2, represents a volume of separation from that nuclei that's on average further separated from the nucleus. Now, we talked about this with hydrogen, but in general, you increase the separation from those charges, you're going to higher energy levels, right? And so principal energy level number 1 for this thing is lower in energy than principal energy level number 2, because that volume represented for energy level 2 is kind of further separated from the nucleus. And you've got other principal energy levels. You might have the N equals 4 out here, or N equals 3 out here. And so it's got its own particular separation distance. Each of those principal energy levels is divided up into several possible orbitals. For the N equals 1, we've got a pretty tight volume around the nucleus, and there's not a lot of space to share many electrons. And what ends up happening is that you only have one orbital that's allowed to occupy that volume. And that orbital is spherical in shape. And it just kind of houses electrons in that spherical distribution around the nucleus. It's called an s orbital. It's called the 1s orbital. When you get into the second principal energy level, the n equals 2, we're kind of moving to a larger radial separation from the nucleus. There's more volume available, and with more volume comes more room to stick electrons in. And so you go out to this second energy level, and you're going to have more orbitals. The n equals 2 level, we have a 2s orbital. Let's draw this guy again. I put too many protons in there for the n equals 1. N equals 2, you've got this spherical orbital called the 2s orbital. But in addition to that, more volume around that nucleus, we have 3 more orbitals. I'm drawing x, y, and z axes here. So this is x, this is z, and this is y. There are 3 orbitals that stick outside of that. They're called p orbitals, and they have this teardrop shaped distribution of charge. Around, as it lies along each of these axes. And these are called p orbitals. So redrawing this real quick. Got 1 orbital here on the z, 1 orbital on the x, and 1 orbital on the y, and they're called the px, py, and pz orbitals. Anyone want to guess why it turns out that these 3 p orbitals end up we end up being able to draw those 3 p orbitals along the axes, the x, y, and z axes? Why would those electron distributions take those positions?
Because that's how they're oriented.
That's how they're oriented, yes, but it maximizes the separation between the electrons, right? So electrons are negatively charged, and 2 electrons are going to repel each other, and so when they decide what volume of space to occupy around the nucleus, they end up taking whatever volume kind of maximizes their separation from each other. And so we've got 3 orbitals, and the best way to orient those orbitals to maximize their separation is along those perpendicular axes, right? So our p orbitals lie that way. We go out, so just keeping track here. In n equals 1, we've got a 1s orbital. In the n equals 2, we have a 2s orbital and 2 p orbitals, 2px, 2py, and 2pz. We go out and we build the n equals 3 level. Now, kind of moving outside to an even larger radial separation. This isn't supposed to be the exact number of charges, I'm just throwing some charge in there. You start off with a 3s orbital. Also on top of that, you have your p orbitals. as we've moved out further away from that nucleus, we're occupying a larger volume. It turns out that there's kind of some room to shove some more electrons in this region out there at the larger radial separation, and that gives rise to additional orbitals that are called d orbitals. So we've got, for the n equals 3, we've got the 3s, we've got the 3px, 3py, and 3pz, and we also have 3d orbitals. And it turns out that there are 5 different z or d orbitals, and if you can imagine, the d orbitals are just oriented so that they occupy the spaces in between the p orbitals. You can take a look at your graph and you can see how those d orbitals align, but it's just a question of what volume is available for electrons to come in from the outside and approach the nucleus. If you look within one principal energy level, the rule is that the lowest energy orbital is going to be the s orbital. The second are going to be the p orbitals, and the third are going to be the d orbitals. The rule is that when you're putting electrons into these orbitals, they're always going to occupy the lowest energy orbital first. And so an s orbital within one principal energy level, an s orbital would be filled first, followed by a p orbital, and then followed by a d orbital. There's a little bit of a twist to that that we're going to approach later, but for now just remember that lowest energy orbitals get filled first, s is the lowest, p is the second highest, d is third place. So I'm not sure how much of this to go into because I'm not sure how much they want you to learn in lecture, and I don't want to confuse things too much, but I'll talk about it for just a second. There's a orbital angular momentum quantum number, and that number gives rise to the number of different orbitals that are present in a particular subset of orbitals, like our s, our p's, and our d orbitals. How many? It gives rise to degenerate orbitals, is what I should say. Orbitals of degenerate energy. And it has to do with magnetism. We won't go into too much depth right now, but anytime a charge is moving in kind of an orbital motion, it creates a magnetic field. Have you guys heard about this in physics yet? You have? So if a charge, could be a minus charge, could be a plus charge, it doesn't matter, but if a charge is moving with circular motion, or motion that's comparable to circular motion, if it's moving in a wave pattern, there's going to be a curvature to its path. And there's a rule called the right-hand rule that describes the magnetic field that's generated when a charged species is moving in a curved path. And the rule is you trace the path of the electron or the charge with your right hand, and you wrap your fingers in the direction that the electron is moving in, and the position of your thumb will show you the direction of the magnetic field that's generated by that curved path. And so an electron, you can imagine in an orbital, has some, it's a wave function, but it's still, you can think of it as having like a circular motion of sorts, or a curved motion. And so it's generating a magnetic field. When you have a spherical orbital like this, the net sum of the motion of the electron results in, even though the electron is moving in kind of circular path, because its paths are kind of evenly, symmetrically distributed over a spherical volume, it gives rise to zero magnetic field for that electron that's in the s orbital. And so we call its angular momentum quantum number 0 to indicate that. When you get into these p orbitals, they're not, each individual p orbital is oriented along a particular axis, and the path of that electron is not, spherically symmetric. And so each of those orbitals will, in fact, generate a magnetic field. We assign, for these p orbitals, an angular momentum quantum number of 1. You get into d orbitals, you start looking at those guys, and those paths are all over the place. We give those guys a quantum number of 2, and then there's such things as f orbitals, and they have a quantum number of 3. There's a rule that for any orbital, any set of orbitals that has these quantum numbers, there are multiple orbitals that satisfy those requirements, and those orbitals can have any value that is any value whose absolute or any number whose absolute value is equal or less than the absolute value of the quantum number that we've assigned. So for 1, we have a possible orbital with a magnetic moment corresponding to a -1, or a 0, or a +1. With a 2, we can have -2, -1, 0, 1, or 2. And with a 3, we can have -3, -2, -1, 0, 1, 2, or 3. And for 0, we can only have 0. And so the angular momentum is what gives rise to these orbitals of degenerate energy. The s orbital has a value of 0, and there's only one s orbital. The p orbital with number 1 can have -1, 0, or +1 for its orbital angular momentum, and so there's 3 different p orbitals. We get into the d orbitals with quantum number 2, then you can have -2, -1, 0, 1, or 2, and so there's 5 d orbitals. So 1 s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals, and again, that all just falls out of the magnetism, the properties of the magnetism of that particular atom. So we saw that an electron traveling in a circular path generates a magnetic field, and that splits these orbitals, these degenerate orbitals, into different compartments. An electron in an orbital generates a magnetic field, but also an electron that's just free has a quality called spin, which indicates that if you take your electron as a basketball and you stick it on the tip of your finger and you start give it a spin like those, whatever those guys are called, Harlem Globetrotter guys do, then you can kind of think of your electron as having that property as well. Well, when that charge is simply just sitting still and spinning around, it obeys sort of the same rules of magnetism, in that there's a B field associated with that electron's spin. There's a rule that says that within any of these orbitals that we have, we can pair 2 electrons as long as they have opposite spins. And so you take one electron that's spinning in one direction, it's generating a B field this way. You're allowed to stick another electron in that orbital but it has to have an oppositely aligned spin. In that case, the magnetic fields generated by those two electrons cancel, and the paired electrons have a zero spin magnetic moment. And so what we're going to do right now is we're going to practice building up atoms based on our different orbitals, the energies of those orbitals, and the properties of spin. There's one other thing that I need to tell you, and that is that when you have electrons, or when you have orbitals that are of the same energy, let's say we have p orbitals. I'm going to draw boxes here representing a px, a py, and a pz orbital. Let's say we've got 4 electrons that we need to stick in these orbitals. The question is, in what sequence do we add these electrons to the orbitals? We could, well, we can't, but I'm going to say we could. We could draw it as 2 electrons being placed in the px, and 2 electrons being placed in the py, and 0 electrons being placed in the pz. Based on what I've told you so far, there's no reason we shouldn't be able to do that. That is not actually allowed by nature. What nature wants to see happen, and this all gets back into rules of magnetism, is it wants to see 1 electron placed in each orbital of degenerate energy first, until all of those orbitals have 1 electron, and then if you still have excess electrons to place, you can start pairing those electrons into orbitals. And the reason, a way that you can think of this is, it has to do with electrostatic repulsions. So we said that electrons are of the same charge, and they're going to repel each other. So anytime you want to try to cram 2 electrons in the same space, there's going to be an energetic penalty, right? And in nature, we want to do we want to go to the lowest energy first. We don't want to generate these high energy situations if we don't have to. And so we wouldn't fill these orbitals like this, where we've got 2 filled orbitals and 1 that's not filled, because we just paid a high energetic debt to cram those 2 electrons or 4 electrons into 2 separate orbitals. We're going to spread them out first, and then once there's no other space available, we'll start pairing them. Also, if you'll notice, when I first drew this, and I placed my first 3 electrons, I drew all of these guys with the arrow pointing up. The direction of the arrow indicates the spin of the electron. It turns out that when you're running calculations on the absolute energies of these molecules, that the lowest energy state is found when all of the electrons in degenerate orbitals have the same spin orientation. And I'm not going to try to argue for that calculation right now, or maybe even next year, but just take my word for it. The lowest energy state is when all of those spins have the same orientation. So, let's start building some species. We're going to learn a couple different nomenclatures, or different mechanisms of communicating an electronic configuration for a particular species. I messed up drawing the periodic table earlier today, and these kids in my class almost threw me out. I don't memorize things. That's what we have books for. right, so that's a rough image of a periodic table. So we're building this periodic table. Remember, each subsequent atom type has one additional proton in its nucleus. That's how we differentiate one atom from another, is the number of protons in the nucleus. We're building these guys up, and with each proton, we need to have an accompanying electron, and we need to be able to write the configuration. There's two ways to write a configuration. Mechanism one that you guys learned is to name the orbital and occupation number. So for instance, if we were going to build hydrogen here, H is 1s because it's the first s orbital that we encounter, that low energy s orbital, and it has one electron in it. So we name that 1s1. Helium, we call that 1s2 because we're still in that low energy s orbital. We're not going to fill anything higher energy yet, but we pair up that second electron. You can write the configuration this way, or you can make a little box and put the name 1s on that box and draw an arrow for each electron in that orbital. So for hydrogen, you'd have a box named 1s, and for helium, you'd also have that box named 1s. In hydrogen, you'd have one arrow, and in helium, you'd have two. So you can build up, or you can identify the atom by drawing a box for each orbital and using arrows to show the number of electrons. The cool thing about this notation with the boxes is that it allows you to communicate a little bit more about what the spin of that electron is. You'll notice that this nomenclature over here doesn't say anything. It says something about occupation number, but it doesn't say anything about the individual spins of the electrons. There's a shorthand notation that you can use. Let's say that we're trying to give notation for this species right here. What's this guy? Is this neon?
Yeah.
Noble gas? Shamefully, I've been doing this for like 15 years. Okay, that's an exaggeration, like 10 or 12. And I don't remember the periodic table. I have to look it up. Okay, so we got neon over here. Let's say that we're trying to build this element right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15 electrons that we got to place in this box, right? So 15 electrons have to go in here. We could write this out longhand. We could say we got 1s2, 2s2,